Okay, before we get started today on this lesson 14.2, there are a couple of files that you can find in Canvas. I've organized it under the Files folder, and then if you go in there, you should find a folder that's called Chapters 12 through 14. You should find three files in there that are labeled 14.2. There's two of them for 14.2 and then one for 14.3. It'll be beneficial if you can print those out, and then as I'm going through them, you can just write on them and take your notes that way. One of the files looks like this one. It's about derivative rules, and this is just kind of a reminder of some of the rules that you learned in Calc 1. And so the very first thing I want to talk about is the definition of the derivative. All right, the definition of the derivative from Calc 1 is that the derivative is the limit as h approaches 0 of f of x plus h minus f of x all divided by h. Okay, by definition, that is just the limit definition of the derivative. All right, then we got several rules along this left-hand column that deal with kind of general cases. What if you take the derivative of a function, and this function is in the form of a constant times a function? All right, well, I think that it's fairly intuitive that all you're going to do is take that constant and you're going to multiply it by the derivative of the function. Okay, and then the derivative of the sum of two functions. All right, again, I think this is fairly intuitive that you're going to take the derivative of f and then take the derivative of g, and you're going to either add them or subtract them. Right, so an application of this would be like to take the derivative of a polynomial function that has more than just one term. Right, so the first two there I think are fairly straightforward. When you get to the product rule, it gets a little bit messier. And the product rule says that when you take the derivative of a function that's in the form of a product of two functions, you take the derivative of the first times the second plus the first times the derivative of the second. All right, and when you took Calc 1, you may have learned this in a different order, and that's fine. Okay, you can put these in any order you want. It's just multiplication and addition, and they are commutative. So whatever order you learn these in is fine. Okay, I do it this way because when you get to the quotient rule, the numerator on the quotient is the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator, and then all divided by the denominator squared. Okay, some of you may have remembered this as, what is this, d high, I don't remember how it goes, d high low minus high d low divided by low squared. Right? You can tell that that's not the way that I usually do it, but this is going to be the derivative of a quotient, and the reason I do it in this order is because if you compare that to the product rule, the numerator is almost exactly the same. It just has a subtraction instead of an addition in it. All right, and then the chain rule is an application where we've got the composition of two functions, one function kind of tucked inside of another. And when we take the derivative of this, we're going to take the derivative of the outside with respect to the inside function left intact, and then we're going to take that and multiply by the derivative of the inside function. Okay, that's the chain rule, and you'll run into that quite often. Okay, so hopefully these are not very new to you, that you've seen these in Calc 1 and you're pretty familiar with finding derivatives of functions that are in that form. And then we got some particular kinds of functions, like a power function. The derivative of x to the n, the rule is hold down the exponent, multiply by x, and then decrease the power by 1. Right, the derivative of e to the x is an easy one. Its derivative is equal to e to the x. And then if you've got something that's not e raised to the x, like 2 to the x or 3 to the x or 4 to the x, the rule is to take the natural log of the base and then times the base to the x power. All right, so e to the x is actually a special case of this because the natural log of e is 1. And then the derivative of a natural log is 1 over x. Okay, so you should know those. Those should be familiar to you. If not, make sure that you spend some time rememorizing those. And then the trig functions, I think you should be expected to know these three. The derivative of sine is cosine. The derivative of cosine is negative sine. And the derivative of tangent is secant squared x. And then the inverse trig functions, you don't run across these as often, but the derivative of inverse tangent is 1 divided by 1 plus x squared. And the derivative of inverse sine is 1 divided by the square root of 1 minus x squared. Right? And again, we're not going to see those as often as we see some of the other ones. All right, so let's take a look at a couple of functions then and see if we can find their derivatives. Okay, these are just on the second page of that first handout. It says, I think 14.2 derivatives rule or something like that. All right, so the first one is just 3 sine of x. Okay, so this is just the constant multiple rule. So the derivative of this is just going to be 3 times the cosine of x. All right, that one's a piece of cake. Okay, the second one, all right, I'm going to go across here. The derivative of cosine of x squared plus 3x. This is an example of using the chain rule. So the outside function is the cosine function, so we take care of it first by taking negative sine, and then we leave the inside intact, and then we multiply that by the derivative of the inside, which would be 2x plus 3 using the power rule. Okay, so that's an application of the chain rule. When you get to number 5 is a combination of the product rule and also the chain rule. So I'm looking at this as, here's a function multiplied by another function. So the product rule says take the derivative of the first. So the derivative of the first function is e to the 5x. Okay, and then applying the chain rule, this is 5x is tucked inside, so we multiply by the derivative of that, times the cosine of x to the third, so we leave the second function alone, and then we add to that the first function, and then times the derivative of the second one, and this is going to be the chain rule also. It'll be negative sine of x to the third, and then I got to multiply that by the derivative of x to the third, so I'm running out of room here, is 3x squared is what would go inside there. All right, so again, the product rule with some chain rule along with it. All right, so if you're watching this, these are the 3 that I did in class with the other sections, and it seemed like at this point people were pretty comfortable with finding these derivatives. So I'm going to leave the other 3 for you to kind of do on your own. Okay, this one, you can do this a couple ways. You could rewrite this as x to the negative 1/3 times cosine. You could write it as a fraction and use the quotient rule. So you could do several things with this one. And then this one also, you could use the quotient rule on. The square root of x, you probably want to write as x to the 1/2 power and then use the power rule on it. All right, but these are not very difficult to do. And I would also suggest that if you feel like you're not very comfortable with taking derivatives, that you're a little shaky on it, you go back to, I think it's chapter 3 in your textbook, and you go to the very end of that chapter, you can find some review problems, and there's like 100 or so functions there, and they say find the derivative, right? And the odd ones are in the back of the book, so you can double check to make sure that you're on track with those. All right, so that's if you just want some extra work working with derivatives. Okay, so these are all things that we need to know in order to move on and talk about partial derivatives of functions of more than one variable. All right, so if you look at the next handout should look something like this. Right, and I want to pick on this function. It's f of x is equal to 3x plus x squared times y. And the other day we talked about how we can find the partial derivatives, that the partial derivative of this function at 2, 3 is increment the 2 a little bit and leave the 3 alone, and then look at what's the change in the function divided by the change in x in this case. That's the derivative at 2, 3. And then the derivative with respect to y at 2, 3, you're going to increment the y a little bit and then look at what's the rate of change, what's the change of the function divided by the change of h. All right, so for this first problem, the first time, I want to go through this a couple of times. and do it a couple of different ways and kind of build up on the idea that we're going to end up using some of those derivative rules. So we did this in class the other day by letting h be a very small value. All right, and when I evaluate this one, with h is a very small number, I think I've had these done before. Let's see. Yeah. Okay, so for this one, if I wanted to find f sub x at 2, 3, and I wanted to approximate this with a small value for h in here, this is going to be equal to the value of the function, and I'm going to increment the x by 0.01. So this will be f evaluated at 2.01, and y stays 3, and then minus f evaluated at 2 and 3, and then divide all this by the change, which is 0.01. All right, and then you're going to take these two numbers and you're going to plug them in here for x and y. And I'm going to tell you that when you do that, you should get 18.1503 minus, when you plug in 2 and 3 in here, you're going to get 18. And then you're going to divide that by 0.01. And when you do the arithmetic on this, you're going to end up with this derivative is 15.03. All right, so if you think about what this means, as you move in the x direction, the function is going to be increasing at a pretty good rate. At 15 is the slope in that direction. Okay, 15.03 is the approximation. All right, and then if I wanted to find fy at 2, 3, all right, and again, this is going to be an approximation. I evaluate f at 2, and then I'm going to increase the 3 by a little bit, so 3.01, and then subtract f of 2 and 3, and divide all that by 0.01. All right, and then when I put these into my calculator, this is going to give me 18.04 minus 18, and then divided by 0.01. And when you do the division on this, you're going to get, this reduces to just 4. Okay, one thing you should kind of notice also is that this number, and this number, and this number, they're all pretty close together. And the reason they're pretty close together is because this ordered pair, and this ordered pair, and this ordered pair are all pretty close together. All right, so if we put in numbers that are close together, we should end up getting numbers that are fairly close together. Okay? All right, so these are the limits that we would get as an approximation using a relatively small value for h. All right, and like I said in class the other day, I think if I said, how could we improve these approximations, I hope everybody would say, well, let's use a smaller value for h. Okay, so that is really a repeat of what we did in class on 14.1. And I want to kind of keep moving forward here, and let's see if we can improve the tools that we have. All right, and so I want to use the limit definition here, and I'm going to pull down that function. This is still the function f of x and y is equal to 3x plus x squared times y. All right, and I'm just rewriting that because I don't want to have to slide the paper up and down. So using the limit definition, the derivative with respect to x at 2, 3 is going to be, instead of just putting in a small value for h, I'm going to look at this in terms of a limit. It's the limit as h approaches 0. And then it's the function evaluated at 2 plus h and 3 minus the value of the function at 2 and 3, and then divide that by h. And what I want to know is what's going to happen to this ratio as h gets very, very small. All right, so this is the limit as h approaches 0. All right, and then if I evaluate this function at 2 plus h and 3, all that means is take the 2 plus h and put it in for the x's. So this is going to be 3 times 2 plus h plus 2 plus h squared times y, which is 3. And then we're going to subtract the value of the function at 2, 3, And the value of the function at 2, 3 is still 18. And then all that divided by h. Right, now, notice that I can't just plug in h equals 0 because I'm going to end up dividing by 0. So I've got to do something algebraic here. And the algebraic manipulation is basically just to expand stuff up here. So I get the limit as h goes to 0. And as I expand this, I'm going to get 6 plus 3h plus, when I multiply this out, I'm going to get 4 first times the first. The insides and outsides are going to give me plus 4h. And the last times the last is going to give me h squared. All that gets multiplied by 3. And then we subtract the function evaluated at 2, 3, which is 18 again. And we divide all of that by h. And this gives me the limit as h goes to 0. I'm going to clean this up a little bit more. We're going to get 6 plus 3h plus, I'm going to distribute the 3, that's going to give me 12 plus 12h plus 3h squared minus 18, all divided by h. And then you should notice that some things happen here. You got a 6 and a 12 and a negative 18. 6 plus 12 is 18, minus 18, those are going to end up adding up to 0. And we're going to get the limit as h approaches 0. And I'm going to be left with 15h from the 3h and the 12h plus 3h squared, all divided by h. And that's going to give me the same thing as if I factor out an h out of the top, we'll be left with 15 plus 3h over h, and those are going to cancel. And then as h goes to 0, this is 15. All right, so this is the exact answer. This is the derivative at 2, 3 for this function. And if you notice, our approximation up here was pretty close to 15. All right, the actual answer really is 15. Okay, now I'd like to go through this one again, and I'd like to find the derivative with respect to y at the same point. All right, and so let me grab another piece of paper. And there's my function again. And I want to find fy at the same point, and that was at 2, 3. All right, so by the limit definition, this is the limit as h goes to 0. It's f evaluated at 2 and now 3 plus h minus f evaluated at 2 and 3, and then all divided by h, which gives me the limit as h goes to 0. Right, and again, this just means substitute these two numbers in for x and y. So when x is equal to 2, you're going to get 3 times 2 plus x squared is 2 squared multiplied by y, which is 3 plus h, and then minus f of 2 and 3, that's still 18, and then divide that by h. Okay, then we're going to clean it up. So this is 6 plus, this is 4, distribute that, you're going to get 12, and then 4h, and then minus 18, all divided by h, and we get the limit as h goes to 0. And again, you get this 12 and 6 and negative 18 all add up to 0, and you're going to be left with just this, and 4h divided by h, you can cancel the h, and you're just going to get 4 for an answer. All right, so this is the exact answer. It just so happens that we got the exact answer for our approximation also. All right, and we're going to see why that happened. That it doesn't make any difference how small h is. You're going to get 4 for an answer up there, no matter what you do for an approximation. Okay, but here I just wanted to demonstrate the limit definition of the derivative to come up with our two answers. Okay, now here's the problem is this ends up being a lot of work, right? And I would like to make things a little bit more efficient. Okay, so I want to make this a lot easier for me to do these calculations. All right, so if we look at the next page, it says, or let's use what we know about the derivative of a function of a single variable. All right, now, again, I'm going to rewrite the function here. That function was f of x and y, and it was 3x plus x squared times y. Okay, so here's the thing. I know that when I take the derivative with respect to x, and I want to do this at 2, 3, I know what I'm thinking here is that I'm going to start at the point 2, 3, and I'm going to move in the x direction. All right, and as I move in the x direction, y is going to be held constant at 3. All right, so this function really is going to become a function of x and 3. All right, so as I move in the x direction, the slope of the tangent curve, or the slope of the curve, is going to be just depending upon what x is. Right? So imagine me walking in the room in the x direction. Y is going to be held constant at 3, and you're going to end up with going along some kind of a curve that goes up and down, but it's only going to be dependent upon whatever x is, if y is constant. All right, so let's call this function. Notice that this function really is just 3x, okay, plus x squared times 3. This is really just the same thing as 3x plus 3x squared. All right, this function is only a function of x, so let me call that just m of x. It's really just a function of one variable. So if I want to know what is this, the derivative of this function at x at 2 and 3, really all I got to do is take the derivative of m with respect to x, and then just plug in what happens when x is equal to 2. Right? Or another way of saying that easier is just what is m prime of 2? So m prime of x, using my derivative rules, is going to give me 3, and then the derivative of this is 6x. And so m prime evaluated at 2 is just going to give me 3 plus 6 times 2. Guess what? That's 15. Okay, that makes that a lot easier to get to the answer. Okay, and if you go back and look on the previous page, that derivative was 15. All right, and then if we use the same kind of argument here and say we want to find fy at 2, 3, so now we're defining this function that we're going to be moving in the y direction, and as I move in the y direction, x is going to be held constant. Okay, x is going to be equal to 2, and then we let y vary. So as you move in the y direction, the slope of the curve is only going to be dependent upon whatever y is. Okay, so f of 2 and y, if I go back here and plug in, we're going to get when x is equal to 2, this is 3 times 2 plus 2 squared times y, okay, which is just 6 plus 4y. And then that function is only a function of y, so I'm going to call that n of y. And so really to find the derivative of this function with respect to y at 2, 3, all I really need to do is find what's n prime when y is 3. Okay, so n prime of y is going to be just equal to 4. So it doesn't really make any difference what y is. This is going to always be 4. Okay, and if you compare these two answers to what we got on the previous pages, they're either really close or they're exactly the same thing. Okay, so this is getting to a little bit of a shortcut of finding the derivative with respect to x and with respect to y, but so far this is still, we just want to find it at a single point. But what if you're sitting at some arbitrary point on the graph and I want to know what is the derivative in the x direction, what's the derivative in the y direction? All right, so what we want to think about then is what is the derivative with respect to x, but I want to know what that is in terms of x and y. All right, so let's think about this again. This is, I'm going to rewrite the function that f of x and y is equal to 3x plus x squared times y. All right, so I don't have a 2 and a 3 in here. I just have an arbitrary but fixed numbers here. But as I move in the x direction, y is going to be held constant, and it's going to be held constant to whatever this number is. All right, so y is a constant, but it's some arbitrary constant. So when I take the derivative of this, I want to treat y as if it is just a constant, and then take the derivative of this function just with respect to x. All right, so the derivative of this with respect to x, well, the first part's easy. The derivative of 3x with respect to x is just x. I'm sorry, is 3. And then the derivative of this with respect to x is x squared, and then think of this as times a constant. Okay, so the derivative of this is going to give me plus 2x, and then times whatever that constant happens to be. So then if I want to know what is fx at 2, 3, then I can just plug in and say, well, that's just going to be equal to 3 plus 2 times 2 times 3, and you're going to get that this is 15. And you get there a whole lot quicker. All right, and then also, if I wanted to know, well, what's fx at, let's say, 1, 2, well, I don't have to start over from scratch. I can just say, well, let's just plug in. So we get 3 plus 2 times 1 times 2, and you're going to get 3 plus 4 is 7. All right, so at this point, the slope in the x direction is not as steep as it is at 2, 3. Okay? So you got to kind of train your mind that you're going to turn these variables on and off. You know, treat one as if it's a constant, and then the other one as if it's a variable. So if we wanted to do the same thing to find the derivative with respect to y, now I'm going to treat x like it's a constant. All right, so if x is a constant, the derivative of 3x is going to be 0. The derivative of a constant is 0. Okay? So then I want to take the derivative of this, but I want to take it with respect to y. So treat x squared like it's a constant, and you're going to get that the derivative of x squared times y is just x squared. And then if I want to know what is fy at 2, 3, all I have to do is take the 2 and plug it in there, and we're going to get 2 squared, and that's 4. And that's the same answers that we got before. Okay? So taking these partial derivatives is taking the derivative using the rules that you learned from Calc 1, but you got to train your mind to think about the other variable as being held constant. All right, so I've got some examples of these. If you go back to the backside of your derivative page, okay, so we filled in all of those derivative rules. And of course, I can't find that page now. Here it is. Okay, so this is back where we were before. Okay, so the first one is find the derivative of x squared plus y squared. And I want to find out what this is at 1 and 2. All right, and if you remember from the other day, this happened to be 2 and this happened to be 4. Right, and I'm only telling you that because we found those already. All right, now this one is pretty easy, that if you want to find out what's fx of x and y, again, we're going to treat y like it's a constant. So this is the derivative of x squared is 2x, and the derivative of y squared is 0. All right, and then if you want to know what is the value here, you're going to plug in 1 for the x, and you're going to find that fx at 1, 2 is going to be 2 times 1, or 2, right, which is what we got doing a whole lot more work the other day. And then fy of x and y, we treat x as if it's constant, and we take the derivative of this function with respect to y, and you're going to get that that's 2y. So fy at 1 and 2 is 2 times, and then plug in y is equal to 2, and you're going to get 4. Right? And that checks out also. Okay? So if I want to know what is the slope at any point, all I got to do is plug into these two expressions, and I've got the slope in the x direction, the slope in the y direction, as a function of whatever x and y are. Okay? All right, this one is a lot like the one that I did initially, so I'm going to skip this one for now. And I want to go down to this number 3. And remember that we talked about this notation was the partial derivative of f with respect to x. This means the same thing as fx at xy. This means the same thing as fy at xy. So the partial of f with respect to x is the derivative of this function with respect to x. All right, so if we think about y as constant, the derivative of 3xy will be 3 times y, and the derivative of y cubed with respect to x is 0. The partial of f with respect to y, treat x like it's a constant. The derivative of this will be 3x, and the derivative of y cubed is 3y squared. Okay, so that makes it a whole lot easier to get to those derivatives. All right, now let's amp it up a little bit. So we got the partial of f with respect to x. Okay, I think that at this point it'd be nice if you just pause the video, try to come up with an answer on this one, and then once you come up with your answer, then let the video go and you can kind of check to see if you're right. All right, so I'm not going to pause here. I'm just going to go on. So the derivative of this is going to be an application of the chain rule. So the derivative says take negative sign of leave the stuff inside alone, and then take the derivative of what's inside with respect to x in this case, and you'll get 3x squared times y squared. And that's an application of the chain rule with partial derivatives. All right, and then if you take the partial of f with respect to y, it's going to start out the same way. You're going to take the derivative of cosine, and you leave what's inside alone, and then you're going to multiply that by the derivative of what's inside, but this is with respect to y, and that would be 2x to the third times y. Okay? All right, again, on this last one, number 5, it's be kind of useful for you just to pause the video, let me work through it, and then you can check your answer. All right, so the derivative of this one is you've got two functions multiplied together, and within those two functions it looks like you've got some chain rule going on. So to find fx of x and y, I'm going to take the derivative of the first function, and so that'll be cosine of 3xy squared times the derivative of 3xy squared with respect to x is 3y squared times the second function, e to the 2x plus 5y, plus the first function, sine of 3xy squared times the derivative of the second. The derivative of an exponential function is e to the power. And then using the chain rule, we're going to take the derivative of this with respect to with respect to x, and you're going to get that that derivative is 2. Okay, it comes from the 2x. The derivative of 5y is 0 with respect to x. Okay, so the derivative of the first function times the second plus the first function times the derivative of the second. And I think if you can get that one, the other one is going to follow kind of the same way. Take the derivative of sine, that's cosine 3xy squared, but now I'm going to take the derivative of this with respect to y, so 6xy, e to the 2x plus 5y, plus sine 3xy squared times the derivative of e to the 2x plus 5y is e to the 2x plus 5y, and then times the derivative of that with respect to y is 5. Right, and it's kind of a mess, it's all kind of thrown together, but it's best if you just leave that unsimplified at this point. I think if you look these up in the back of the book, they're probably going to try to simplify as much as they can by pulling out common factors, like the e to the 2x plus 5y is a common factor and everything. Okay, so I'm hoping that that gets you going on finding some of these derivatives. I've got a couple more examples here that you're free to work through, but I want to skip ahead to this one, okay, where we've got a function of 3 variables. All right, and so if you remember, when we talked about functions of three variables, I said it's probably best if you think about functions of three variables as a temperature function. All right, so this function is going to tell me the temperature at any point in the room. And so if I wanted to know what is fx at some point, we'll call it at x, y, z, and I wanted to know what is this thing going to measure. Right, well, this is going to measure kind of the same idea that we had before. If I'm at some point in free space and I move in the x direction, this is going to tell me how fast the temperature changes as I move in the x direction. Right, and then as I move in the x direction, what's going to be true about y and z is they're going to be held constant. Okay, so this isn't going to be anything that's really different. This is just going to be taking the derivative of a function of three variables with respect to x. So we're going to treat y and z like they're constants. So to take the derivative of this part, you're going to use the chain rule. So you'll have 2 and then 3xy plus z raised to the first power, and then times the derivative of what's inside with respect to x, and that would be 3y. Plus the derivative of this with respect to x is 4x, y to the third, z to the fourth. And then fy is the derivative with respect to y, so consider x and z are constant. So we're going to take the derivative using the chain rule again, so we're going to end up with 2 times 3xy plus z raised to the first, and then times the derivative of what's inside with respect to y is 3x, plus the derivative of this with respect to y. So use the power rule on y to the third, and you're going to get, 6x squared, y squared, z to the fourth. Okay, and then fz of x, y, and z. This would tell me what's the rate of change in the function as you move in the z direction. And so it's going to be 2 times 3xy plus z times the derivative of what's inside with respect to z. So the derivative of this is going to be 0, and then the derivative of that is just 1. And then the derivative of what's left with respect to z would be 8 x squared, y to the third, z to the third. All right, so taking partial derivatives of a function of three variables is really nothing different. It's you use the same concepts, but you hold two of the variables constant and take the derivative with respect to a given variable. All right, so now if I just plugged in an ordered pair or an ordered triple here, you could tell me what is the rate of change in any of these three directions. Okay, so again, you've got to remember your derivative rules. And then really this is just an exercise in can you look at a function of more than one variable and kind of turn on and off that one of them is the variable and one of them is held constant. And if you can do that and then still apply all those derivative rules, that is really the goal of section 14.2 is to be able to find all those partial derivatives using that technique. And then you don't have to use the limit definition, and we don't have to worry about trying to find some approximations. This is a much, much better technique. Okay, so you guys should be working, after watching this video, you should be able to work through 14.2 homework. Again, work through that after watching this video. If you got questions, you'll have some time next week to ask questions about the stuff. And then be watching, or you can probably go on and the 14.3 video is going to be available there pretty soon if it's not there right now. Watch that one, and then you can get through 14.3 homework as well. Right, and then also, well, you should just be caught up through 14.3 by the time we meet again. Okay, thanks. Have a great weekend, and I will see you next week sometime. All right, bye.